All right, let's dive right into something that sounds like pure science fiction: quantum computing. We're talking about this immense, almost cosmic power. But what if I told you that you could start programming the very building blocks of the universe right now? Let's see how. So here's the big question, right? How do you even begin to program a computer that exists in this state of pure possibility? I mean, we're not dealing with simple ones and zeros anymore. We're talking about quantum bits, qubits. That can be a 1, a 0, or somehow both at the exact same time. How on earth do you control that? Well, what if the answer was surprisingly close to home? Yeah, you heard me right. From your laptop. The power to actually experiment with the weirdness of quantum mechanics isn't locked away in some high-tech lab anymore. It's for anyone with a computer and, a bit of curiosity. But this brings up a pretty fundamental problem: the quantum access problem. Look, real physical quantum computers, they're incredibly rare, super expensive, and honestly a little delicate. So how can anyone learn to program in this quantum world without one? The answer, it turns out, is brilliantly simple. The solution is to simulate. Just think of it like a flight simulator, but for quantum circuits. You wouldn't want your first time flying a jumbo jet to be, the real thing. You learn the controls, you test out maneuvers safely on the ground first. We can do the exact same thing with quantum programs, running them on our everyday computers. And the best tool for the job? It's called Qiskit. Okay, so let's get to know our quantum flight simulator, Qiskit. This is the piece of software that really bridges that huge gap between the wild, mind-bending theory of quantum mechanics and the practical reality of sitting down and writing code. So what is Qiskit? It's an open-source software kit, or SDK, straight from IBM. And the open-source part is huge. That means it's totally free for anyone to use and tinker with. Even better, it works with Python. That was a really smart move, because Python is one of the most popular languages on the planet. It has this massive, helpful community and pretty gentle learning curve, which makes diving into quantum computing as accessible as it's ever been. And the whole process? It's wonderfully straightforward. There are basically 3 steps. First, you build. You create your quantum circuit, which is just like writing out a set of instructions. Then, you simulate. You run those instructions on a virtual quantum computer right on your machine. And finally, you analyze. You look at the outcome, you visualize the results. Build, simulate, analyze. See? It's a really simple workflow, so let's actually try it. All right, we're going to jump right in and create one of the most famous, most fundamental things in all of quantum physics: a Bell state. This is the perfect example to see 2 of the wildest quantum properties in action: superposition and entanglement. All we're going to need are 2 qubits. That's it. Our whole goal here is to manipulate them just so that their fates become intertwined in this very specific, almost spooky way. And it all starts with just 2 little lines of code. Okay, here's our first line of code, qc.h of 0. Now this applies what's called a Hadamard gate, that's the H, to our first qubit, which is qubit 0. In the quantum world, a gate is just a basic operation, like a fundamental command. And this command, this one, is the key that unlocks all that quantum potential. And just like that, with one command, we've put our first qubit into a state of pure potential. This is superposition in action. Before this gate, our qubit was a definite 0. Now it exists in this balanced, ghostly state of being both 0 and 1 at the same time. It's pure possibility. So next up, we need to link it to our second qubit. And here's the second command, qc.cx01. This is a C-NOT, which stands for Controlled Not Gate. And what it does is it links our 2 qubits together. You can kind of think of it as a simple if-then statement. If our first qubit ends up being a 1, then flip the second qubit to a 1. But here's the magic. Since our first qubit is already in that weird state of being both 0 and 1, this simple link creates something truly extraordinary. And that is entanglement. The 2 qubits are now basically a single system. Their fates are completely intertwined. If we measure the first one and find out it's a 0, we know instantly the second one is also a 0. If the first is a 1, the second must be a 1. And this is true even if they were on opposite sides of the galaxy. It's wild. So after all that, what does our simulation actually show us? And there it is. It's exactly what quantum theory predicts. When we run this simulation thousands of times, what do we see? We find the qubits in the 0, 0 state about half the time, and in the 1, 1 state the other half. We never get 0, 1 or 1, 0. This chart right here is the payoff. It's the visual proof that our two simple lines of code actually worked. We successfully created an entangled Bell state. Okay, so creating a Bell state is a fantastic start, but it's really just that, a start. The whole point of the Qiskit ecosystem is to scale this up, to move from these simple hello world examples towards solving problems that are just impossible for today's computers. We're talking about things like discovering new medicines or creating revolutionary materials. Let's see how that path works. So Qiskit gives you two really powerful options. For learning and doing quick tests, you can use the Air simulator right on your own machine. It's fast, it's convenient, it's what we just did. But when you're ready for the real deal, you can send that exact same code up to the IBM Quantum Cloud and run it on actual real-life quantum hardware. And that's where you face real-world challenges like noise and errors, which honestly is a crucial step in learning how these incredible devices truly operate. And listen, as your circuits get more and more complex, you can't just keep them all in your head. It's impossible. That's why visualization tools are so important. Qiskit lets you literally draw out your circuit diagram so you can see every gate, every qubit, and how they're all connected. It makes it so much easier to spot mistakes and really understand the logical flow of your program before you even hit run. So what does this all mean when you step back and look at it? It means that this revolutionary, world-changing technology isn't being cooked up in secret behind closed doors. No, it's being built out in the open by a whole community of scientists, developers, and even hobbyists, all working together. All right, so let's just quickly recap the main points here. First, powerful tools like Qiskit are the bridge, turning abstract quantum theory into actual practical code you can write. Second, simulation is our sandbox. It lets us experiment and see how quantum states evolve, safely. Third, cloud access means anyone can get their hands on real quantum hardware. And finally, those visualization tools are absolutely essential for making sense of it all. It's a whole new frontier of computing, and the doors are wide open. And that really is the question I want to leave you with. For the first time in human history, the ability to actually program the quantum world isn't limited to a handful of physicists in a lab somewhere. It's in your hands, on your laptop. The tools are here. The access is here. The only real limit now is our imagination. So what will we build?